So today we start a new chapter, which is a story of Teichmüller space. Teichmüller space of punctured surfaces. So our motivation is to construct a basic algebraic system, the system which allows to construct representations of the mapping class groups. And we will end up with a basic algebraic system by considering the Teichmüller space. So as last time we consider a surface of finite type, the complement of a closed oriented surface of genus G of S points called punctures. And as we imposed last time, we assume that this quantity is positive, which means that we have at least one puncture, and the Euler characteristic of the surface is negative, which means that it admits a hyperbolic metric. Yeah, and so if we recall the very first lecture about the motivation, then we talked about Chern-Simons theory. And in that Chern-Simons theory, there is a phase space, so-called phase space, which is a space of flat connections. And the space I'm now going to define is exactly that kind of phase space, which is called M of sigma. And it is nothing else but the space of group homomorphisms from pi1 of the surface. But to be more precise, let me fix a base point. So in the group PSL2R. And we impose here the condition that the holonomies around punctures are parabolic. Parabolic holonomies around punctures. The space, and we identify two equivalent representations, PSL2R, where this group acts by conjugations. So rho is equivalent to rho tilde if there exists a G in PSL2R such that rho prime of gamma is equal G rho of gamma G minus 1 for any gamma, for any class of gamma in pi 1. So so here it's important to point out that one and the same G serves all gamma. So that's the equivalence, which is here. Yeah, and just as a side remark, so the automorphism group of pi 1 acts on that space just by precomposition. So if we have a G, an automorphism, and a representation, then we just compose it like this. So let me put it a class of representation. Okay, so this is the phase space. In principle, we should be, if we want to stay in contact with Chern-Simons theory, then in principle, we should work with this space. But we will not do that, so we will just work with one piece of that space, which is called Teichmüller space. Teichmüller space. So it is called tau of sigma, which is a connected component of M sigma. Connected component given by discrete phaseful representations. Why a-connected? Because actually there are two connected components which both correspond to discrete phaseful representations. And they are homeomorphic, and they differ from each other by the change of orientation of the surface. So we pick up one of those and call it a Teichmüller space. And due to phasefulness and discreteness, the image of the corresponding representation can be identified with the fundamental group of the surface. So there is a really geometry is going on around any point of the Teichmüller space. So if we pick up a point in Teichmüller space, then the image of pi 1 so it is a gamma rho PSL2R. So it is a discrete subgroup of PSL2R, which is gamma rho is isomorphic to pi 1 of sigma 0. And correspondingly, the surface sigma is identified with the quotient space of the hyperbolic space with respect to this subgroup. So the surface becomes a hyperbolic surface, which means that we have all the geometry on sigma due to the right-hand side of this equality. So we have geodesics, lengths, areas, and all that on our surface. Yeah, and then maybe I should make a remark. maybe two remarks concerning there are very different interpretations of the Teichmüller space. And there is one which I'm going to mention here, which is more geometric. Here we just use the representation theory. So more geometric definition of Teichmüller space is as follows. So we call marked surface is a pair. F and X, where X is a hyperbolic surface okay, marked surface of type S, not S but sigma, we denote it. So where X is a hyperbolic surface, and F is a homeomorphism between sigma and X. This is not V but R. Hyperbolic surface, homeomorphism, and then we impose the equivalence relation. And two marked surfaces, F1, X1, and F2, X2 are equivalent if and only if X1 okay, what we can do, we can make a composition F1 composed with F2 inverse. And this maps X2 to X1. And we say that two marked surfaces are equivalent if this composition is isotopic to isometry. Pick to an isometry. So these two hyperbolic surfaces. So we can talk about isometry between them, so the bijective correspondence which preserves the distance. And we demand that the two marked surfaces are equivalent if this composition, which is a priori just a homeomorphism between two surfaces, is in the connected component, can be connected by a continuous deformation to an isometry. Then we say that these are equivalent. And then, so the Teichmüller space is identified with equivalence classes. Classes of marked surfaces of type sigma. And yeah, so this is more geometric picture. And here we can see that the mapping class group X. Right, this is the second remark. So the mapping class group of our sigma of our surface X on tau sigma, if we use this interpretation, why? Because we can precompose a marked surface with a homeomorphism. So G Fx is mapped to F composed with Gx. G is a self-homeomorphism of our surface sigma. And then we can apply first this self-homeomorphism and apply the F in the marked surface. Then we get another marked surface. Yeah, so we should talk about the equivalence classes. But on the other hand, in the moduli space, we have action of the automorphism group of the fundamental group. So in fact, automorphism group can be thought also as a mapping class group. At least the mapping class group, there is a homomorphism of the mapping class group to automorphism group of pi1 for clear reasons, because we can map loops to loops by self-homeomorphisms. So action of the mapping class group induces an automorphism of the pi1. And in this way, this action corresponds to, if we compose this action with embedding of the mapping class group into automorphism group of the pi1, then this action is identified with that action. But this is very vast theory with many intricate things, so we are not going to touch anything like that, because our goal is more simple and practical. So we want to end up with some concrete algebraic system which would allow us to quantize in particular and eventually to construct basic algebraic system we are interested in. Okay, so let me just list a few properties of the Teichmüller space. Properties of Teichmüller space. So first of all, what is it topologically? So the first property is tells that this space is homeomorphic to a open ball. Morphic to R power 6j minus 6 plus 2s. Second property is tau of sigma is a symplectic space. With a Weil-Peterson symplectic structure. Symplectic structure. So, from a physical point of view, the symplectic structure is not surprising, because the modular space appears as a phase space of a dynamical system, and in mechanics we know that any dynamical system formulated by minimal action principle eventually we end up with Poisson brackets and symplectic structure. But here this symplectic structure is known independently through pure physical, through pure mathematical studies of the Teichmüller space. And the third property, which will concern us, that the mapping class group of sigma x on tau of sigma by symplectomorphisms. Which means that it preserves the symplectic structure. Okay, so now we go to we are going to study another space, and we will see why later. So it is called decorated Teichmüller space. Decorated Teichmüller space. So what is it? So it is called tilde of sigma. And by definition, it is a set composed of a point of the Teichmüller space and S horocycles, one horocycle for each puncture. So M is a point in the Teichmüller space, and HI is a M horocycle. So if we pick up a point in the Teichmüller space, so we have a hyperbolic surface, and in particular we can talk about the horocycles on that surface. And this HI is the choice of a horocycle around the puncture PI. So we can think of so we have something like this. Then the punctures are represented by as infinite cusps, like this. And HI is something like just some circle which cuts out the corresponding cusp. And then if we move this circle, then keeping the same M, we can move each circle. So then we move in this bigger space. So this is a decorated Teichmüller space. And
sorry, what term did you use for M? We just don't know what word it is.
M is a point in the Teichmüller space. Okay, so hyperbolic structure.
And, sorry, here, yes.
M horocycle. Okay, we don't worry. We will define it. We will come to that because this is concrete thing, and I will define the horocycle in a moment. Okay, so but before I come back to horocycles, so remark that we have a map. We have a projection. Projection phi, which goes from decorated Teichmüller space to the original Teichmüller space, just by forgetting the horocycles. Okay, so we will keep in mind this fact. And now I'm going to define what is horocycle. So recall, I hope we know something about hyperbolic geometry in the plane. Do you? No? Not at all? Okay. Okay, then hyperbolic geometry. This is I didn't expect that. Okay, but okay. Hyperbolic geometry in dimension 2. Okay, so what is it? So H2 is a upper half space. So it is a Z in C such that imaginary part of Z is strictly positive. So as I said, the two-dimensional hyperbolic space is this. And the isometry group isom plus of H2. Plus means that we talk about orientation preserving isometries. Is identified is P SL2R, which acts as follows, which acts by fractional transformations as follows. So G acting on Z is given by AZ plus B, CZ plus D, where G equal A, B, C, D. But do you understand what this P means here? Okay, so for those who forgot, I recall that this is the quotient group of SL2R with respect to plus minus 1. And so this G is in there. So 2 by 2 matrix of unit determinant up to sign, overall sign. So if we write it minus A, minus B, minus C, minus D, it is the same element in that group. Okay. So and you see that in this action, if you change simultaneously the signs of all 4 elements, this fraction doesn't change. So we really have an action of PSL2R group. So that's an isometry group. And then using already this fact, you can deduce what is a metric. But I'll say just what are the geodesics. So geodesics, this is not a course on hyperbolic geometry. Sorry to be sketchy. So we will not derive here anything. So geodesics are given by half circles perpendicular to real line, or vertical lines. So the half circle perpendicular to the real axis. So we put a point, pick up a point on the real axis, and pick up a real number, radius, and draw a circle centered at here. So this is the analog of the straight line in the hyperbolic geometry. So this is one type of geodesics. And another one, just we draw a vertical line like this. It's also a geodesic. And it can be thought as a circle of infinite radius. And now, yeah, so maybe how we measure the distance. So the Riemannian metric, metric is given by length element ds squared, which is dx squared plus dy squared divided by y squared, where z is given by x plus iy. So the condition that the imaginary part is strictly positive enters here. So we divide by y, so y should be positive here. And in particular, we can measure the length of a vertical segment. This is the easiest calculation in this geometry. So example of calculation. So imagine we have 2 points I A and I B. So, and we are interested what is the distance. So the distance between I A and I B. So what we do? So we accept that if we accept that the vertical line is a geodesic which passes through these 2 points, then we should use this tensor to calculate the length. So this distance is equal integral of dy over y. So ds equals 0. Okay, so ds equals dx equals 0. So ds squared is dy squared over y squared, and we should integrate the length element from IA to IB, so which is dy over y. This is z, right? So which corresponds to integration of y from a to b. So we end up with a formula logarithm of b over a. We can put the absolute value, but if b is greater than a, then we can remove the absolute value. But anyway, that's a length, hyperbolic length of that segment. Okay, so that's as concerns geodesics, and then horocycle. What is horocycle? Horocycles. So I will define them just like geodesics. So if geodesics are given by either by half circles or vertical lines, then horocycles are given by either circles tangent to real line. And second, horizontal lines. That's an example of a horocycle. And that's another horocycle. But of course, they have some geometric meaning. First of all, set of geodesics, of course, is preserved by the isometry group. So any geodesic is sent to another geodesic by any element of the isometry group. And likewise for horocycles, any horocycle is mapped to another horocycle by arbitrary isometry element of the isometry group. And another property is that if we look at all geodesics which depart from the tangency point of a given horocycle, like, for example, a vertical line or a circle like this, or a circle of a smaller radius, then simple geometric fact tells us that this horocycle is always perpendicular to those geodesics. So these are right angles. And there are many properties like that. So I'm not going to talk about them, and presumably I don't know most of them. But we will use, of course, something. So horocycle already we are using in the context of decorated Pech-Miller space. And let me say what is meant that we choose a horocycle around the puncture. So the puncture in the when we have a hyperbolic surface, then so the hyperbolic surface. What does it mean that we have a hyperbolic surface? It means that we have a X, which is a quotient space of that space with respect to some discrete group. And then, so any geodesic in a hyperbolic surface is represented by a geodesic in the upper half space. And any horocycle in here is represented by a horocycle in H2. And that means that, so suppose that, now let E be an isotopy class, the isotopy class of a simple path running between two punctures. Two punctures possibly coinciding. So we can have a E be the non-trivial. So non-trivial means we assume that if it runs between one and the same puncture, then it is not trivial, which is isotopic to point. So assume we pick up such a path.
Sorry, what is simple?
Simple means that in its class there is a representative without self-intersections.
Okay.
So then, I don't have picture, so let me try to draw. So we have something like this, 4 punctures, some genus, and then we can have something like this, so E. A path, and then there exists a unique geodesic in E. What? Something wrong? No? So we pick up a such class, okay, and then so the geometry makes it possible to choose a unique representative in that class, which is a geodesic with respect to that structure. Okay, so sigma, we pick up a hyperbolic structure on sigma, and then so in that class we have a geodesic. Okay, and then in the decorated case we have also these horocycles. And now, what does it mean in concrete terms, this configuration? So in H2, we have a lift of that geodesic. So any geodesic is a half circle or vertical line. So assume that it is a half circle. So we have this. And then the 2 horocycles, which correspond to those little circles, correspond to horocycles based at the point to which arrive this geodesic. So we have one circle tangent at that point, and we have another circle tangent at that point. So this is, let me put the HI, HJ. So then we have a HI tilde, HI, J tilde. And then the fact that we demanded this to be non-trivial means that we really have such configuration with a geodesic which is uniquely defined by the picture. And there exists a unique geodesic E tilde in E, and this is a E tilde. And of course, here we can vary these horocycles here. And this corresponds to varying a point in the decorated Teichmüller space. So the fixing those circles corresponds to fixing a point in the decorated Teichmüller space. But of course, we can pick up another representative in H2. Then there will be a group element in gamma, which stands one representative to another representative, and all that. So, but this picture is most important to understand what's going on and to understand the coordinates, which we will be discussing after the break. Okay, we can make the break now. So let this class I will call ideal arc. Okay, that's the terminology, ideal arc. So in other words, any ideal arc can be represented by a unique geodesic with respect to a given hyperbolic structure on the surface. And now the definition. Let E be an ideal arc in sigma. The lambda length associated to E is a function lambda E, which is defined on the decorated Teichmüller space of sigma with values in strictly positive real numbers defined by lambda E of M tilde. Okay, so this tuple I will call tilde. M tilde is M H1 HS. So which is given by E power delta over 2, where delta is the signed hyperbolic length of the segment of E tilde between the horocycles. Okay, let us try to draw this picture. So we take a E ideal arc, and then we lift it to H2. So we have a geodesic representing this ideal arc. Then we have a pair of horocycles, HI tilde and HJ tilde. And then what we do, we measure this length of that segment between these two intersection points. And this will be, the result will be number delta. And we take an exponential of half of that. And this is lambda length. And the signed means that delta not necessarily positive, because we can have a configuration like this. We have a huge horocycle, like, I don't know, and another big horocycle like this. And then the segment still is here, but this is minus delta. Okay, so we still calculate this length, which is positive, but delta will be minus that length. And in this way, so the lambda length can take any value, any positive real value, because even less than 1 if the corresponding signed distance is negative.
I'm sorry. And if our geodesic is a vertical line, is the length always negative?
No, if it is vertical line, what you will see? You will have a vertical line, you will have a horocycle like this. But what is the endpoint, another endpoint of that geodesic? It's infinity. And the horocycle based at infinity is a horizontal line. So another horocycle will look like this.
Okay.
And then the delta is here, so which is positive in that case. But if it would be there, the distance would be this distance, which would be minus delta. Okay, it is quite the same. And then maybe this is a Poincaré model for the hyperbolic space, upper half space. But you can have a unit disk model where the whole hyperbolic space is concentrated inside the unit disk, and any geodesic now is a circle perpendicular to the boundary circle, and also the diameters. These are the geodesics, and then horocycle still circles tangent to the boundary circle, and in this way you don't distinguish between finite points on the real line and point infinity, just any point on the circle. So you know that real line plus point infinity is a circle, and this circle is identified with this boundary circle in this unit disk model. And then so the picture universal independently of what is a geodesic. Okay. So for calculations, I think that the upper half space model is simpler, while for drawing pictures, maybe the unit disk model is more illuminating. Okay, so that's a lambda length, and then I will give an exercise for next time. Here I will make it as a remark. So I will not write, but I will draw. So we have a configuration like this. And then we can draw one more horocycle, which is tangent to both horocycles here. Okay, we just pick up a horocycle, and now we'll start blowing it until it touches both these horocycles. Then we will get something like this. And now we can measure horocyclic length of that segment. This is not a geodesic anymore. This is a horocyclic segment. And we can measure its length. Because in geometry we can measure length of any curve, not only of a geodesic. And this number is nothing else but the lambda length of that E. So we can just forget about the exponential, just we can define the lambda length as a true length of that horocyclic segment, like here. It is always positive now. We don't have any signed thing. this is exercise. Good exercise in hyperbolic geometry. Yeah, so lambda length is defined now. Yeah, so we approached the main part of today's lecture. So there will be theorem consisting of three parts on which we will base the rest of the course, in a sense. So, but before, let me fix notation. So x power y will mean the set of maps from y to x. Okay, this is a definition. Second notation I will be using, so if x is a CW complex, then x sub I will be the set of I-dimensional cells. Of x. Okay, now a theorem, yeah, which is actually three theorems, but I will put them into one theorem with three parts. And these are famous three theorems of Penner. So the first part is the following. For any ideal triangulation, tau of sigma, the map lambda sub tau, which goes from decorated Teichmüller space to the set of maps from edges of the triangulation to real, positive real numbers. Okay, now I'm heavily using this, all this notation. So this is a set of maps from the edges of the ideal triangulation to real numbers. The map defined by, so let us see, so we pick up a point here. So lambda tau applied to m tilde. So remember that the point here is a hyperbolic structure on the surface, and the tuple of horocycles around each puncture. And now, when we apply this to a point in here, so we should get a function on the edges of the triangulation. So if we apply to an edge E to in ideal triangulation, so this is an ideal arc, right? Ideal arc, but for each ideal arc we define the lambda length. Of m tilde, right? A positive number, the previous definition. So we define the lambda length as a function on the decorated Teichmüller space with strictly positive real values. So this function associates to ideal arc given as an edge of the ideal triangulation the lambda, corresponding lambda length. Okay, that's the function. So, and now the theorem tells that this map is a homeomorphism. In other words, this part of the theorem allows us to identify this space just by coloring of the edges of an ideal triangulation by positive numbers. And this is a bijection. Second part is about what happens if we change the triangulation. So if tau and tau prime are related by one diagonal flip, so this is in tau, and tau prime. So when I say this, it means that these almost identical ideal triangulations, but with only one difference inside a given quadrilateral. So we pick up two triangles, and then the corresponding quadrilateral can be triangulated in two possible ways. So one choice corresponds to tau, another choice corresponds to tau prime. So if we have this, and then we color the sides by real positive numbers. This corresponds to point in a decorated Teichmüller space. Flip and A, B, C, D, E, F are corresponding lambda lengths of M tilde in decorated Teichmüller space. Then there is a relation. Because we have two coordinates due to first part of the theorem. We have two coordinates for one and the same point M tilde, given by the ideal triangulation tau and the ideal triangulation tau prime. And now this second part tells us what is the relation when we change this elementary transformation. Then EF equal AC plus BD. And this is called Ptolemy relation. That's the second part. And third part. So let omega WP be the two-form representing or corresponding to Weil-Peterson symplectic structure. To Weil-Peterson symplectic structure. So we are in the Teichmüller space, because it's a Teichmüller space which is symplectic. Then, what we can do? So remember that decorated Teichmüller space projects down to usual Teichmüller space by forgetting the horocycles. But on the other hand, we have a lambda tau, which identifies the decorated Teichmüller space with coloring of the edges of an ideal triangulation by positive numbers. And now what we can do, we have a two form down here. So we can pull back. So we can compose phi with the inverse of lambda tau. Right? This is a map from the space of r plus to the power tau 1 to Teichmüller space. And now we can pull back the form by that map. And this part of the theorem tells us, gives us an explicit formula for that pullback. This is the sum of all triangles in tau 2, so two-dimensional cells. dA wedge dB over AB plus dB wedge DC over BC plus DC wedge dA over CA. Where T is a triangle, and it has three sides labeled ABC, which correspond to coordinates in that space. So we have this formula for the pullback of the Wield-Peterson form. So you see that these three parts of that theorem make the theory of Teichmüller space on the level of decorated Teichmüller space very explicit and elementary. So we just can work with a tuple of positive numbers associated to edges, and then a simple Ptolemy formula for changing the coordinates if we need to at some moment, and a very simple formula for the symplectic two form. But of course, in these coordinates, it is not non-degenerate because it vanishes along the fibers. So we have a fibers. Okay, so maybe actually I forgot to put in my notes force part. But now I remember this force part also important. So the force part, how to identify the fibers of the map phi here. So that part tells the following. So if so phi of m tilde is equal to phi of m tilde prime, if and only if there exists alpha, a function on the vertices of the ideal triangulation, such that A prime is equal alpha of pi, alpha pj A, where so we have an ideal arc with value A here, and then we have Pi, Pj. So if we can find a function defined on the vertices with positive real values such that all A primes are calculated just by rescaling the coordinates in A, then this corresponds to exactly one and the same point in the Teichmüller space. So that means that this kind of transformation fulfills only the change of the horocycles of the points. Okay, so that's the main theorem. And let me, we are not going to prove it, but I will now give a couple of remarks how it works and what is the idea, for example, of proving the first part. What should I erase now? Can I erase this? No? This? So the inverse of lambda tau is constructed or is described as follows. So remember that lambda tau is a map from decorated Teichmüller space to set of positive numbers on edges. So the inverse means that we should be able to single out a point in here, starting from a coloring of edges of the triangulation by positive numbers. So what we do is the following. So we take a sigma hat. Let sigma hat be sigma be the complement of small open this centered at punctures in sigma. So, for example, if we have a once punctured example, sigma equals sigma 1, 1. So we have a rectangle. This is sigma. And we go to sigma hat, which is a result of cutting out a small disk centered at the puncture. So we have something like this. So the surface with boundary. And then, so for any t in tau 2, so the CW complex tau induces This is a CW decomposition of sigma decomposition tau hat of sigma hat. Okay, so if we have T in tau 2, then we have a corresponding 2 cell in tau 2 hat, which is here we had a triangle, here we will have a hexagon, right? This is T hat. This was T. And then we have short edges and long edges. So this will be long edge, and this will be short edge. Okay, we have constructed new CW complex. And now what we do is the following. We associate parallel transport operators or matrices to each edge of tau hat. Okay, so let me. So we have coloring A, B, C, okay, of the edges of the original. Now we get the truncated triangle, and we orient, for example, a short edge like this, because our surface is oriented, so we choose this orientation. And then what we associate to this short edge is the following matrix: 1, 1, C over AB. For each short edge, we associate this upper triangular parabolic matrix by using the positive numbers sitting on the 3 sides. And for each long edge, we associate a matrix with zeros on the diagonal, and the numbers b minus 1 minus b on the opposite diagonal. And this should be thought as elements of PSL2R. And for example, here I specify the orientation, because the inverse of this matrix is not equal to itself. But here I didn't specify the orientation, because the inverse of this matrix is the same matrix up to sign. So it is a order 2 element in PSL2R. Okay, because if we multiply this matrix by itself, what we get? Everybody knows to multiply 2 by 2 matrices. Minus 1, 0, 0, 0, 0, minus 1. So you see, it is a unit in PSL2R. Okay, so this matrix is of order 2. So we, for any orientation, we put the same matrix. And now, and that's it, effectively. So in this way, we get a representation of the fundamental group of the surface, because the surface retracts to sigma hat, right? Because we removed small disks centered at punctures, but punctures are removed, so they are not in the surface. So our surface deformation retracts to sigma hat. Right? So, so the fundamental group of sigma hat is equal to fundamental group of sigma. And this is a cellular decomposition of sigma hat. And so its two skeleton describes the fundamental group. And so here we describe the matrices we associate to one skeleton. And the only thing we have to make sure that the relations which are associated with the two cells are satisfied. And this choice exactly makes sure that the relations are satisfied. So let us see how. It's an exercise in multiplication of 2 by 2 matrices. Verification of the flatness condition. So we have A, B, C. And so let us calculate this. So we pick up this 0 minus A minus 1 minus A, 0. Then this matrix 1, 1, C over AB. And the matrix B, 0, B minus 1, minus B, 0. And this is multiplication twice of 2 by 2 matrices. Let me not to do that. And the result is minus B over A minus A over B.
I'm sorry, the orientation of short edges is not consistent?
No, because if we change the orientation, we have to put inverse matrix.
Okay, but I mean
But I am going to multiply those, okay, with that orientation, because I'm going to compare this parallel transport with this parallel transport, okay? So that's for the upper parallel transport. And now for lower parallel transport, I will write another product. So what we have here, we have to take inverse of that corresponding to that edge. So it is a 1, 1, 0 minus B over AC times anti-diagonal matrix C and the inverse of upper triangular here, which is a 1, 1 minus A over BC. And I claim, sorry, this is not 0, C. C, and I claim that this product is a negative this one. Please check if to make sure I didn't make mistake. I'm writing this. Okay, so in each hexagon, so we have a flatness condition. So that means that we have a representation of the fundamental group. You pick up a base point, for example, any vertex in the cellular complex. And then for any closed loop, you calculate the product of those matrices, and that represents that loop. And this gives you the first component in M tilde, the part which corresponds to a representation, which will be a discrete faithful, but of course here we don't explain why it is so, but it is so. And how we identify horocycles. So horocycle associated to pi. So what we do? So we have around pi, we have a configuration like this, right? So let me erase. This part doesn't exist. It is cut out. But we have short edges going around. So rho of that gamma is given by some with some number c gamma. Right, according to our rules, we end up with that matrix. And then the hi, independently of the value of ci, is given just by horizontal line, which is a horocycle at height 1. I not maybe good, pj. Hj is given by t plus I. T in the real line. So let me put here some x0 base point. Okay, we can talk about only about the fundamental group as soon as we have chosen base point. So if we put base point here, so this is that's the matrix which represents that loop, and it fixes any horizontal horocycle. This matrix, and we choose the horocycle to be at that height, at height 1. And now, if you try to calculate, for example, you have another puncture here, then in order to identify what is the horocycle which corresponds to that puncture, what you should do, here you have another base point with respect to which the horocycle is given by the same horizontal line, but you have to conjugate it by that parallel transport, which relates different base points. And then in general, you will change your horocycle by applying this parallel transport, so it will be something else. Okay, so that's as concerns the first part. And let me finish with derivation of the Ptolemy relation. So the second remark, derivation of Ptolemy. So what we do, we draw truncated disk like this, and a truncated disk like this. Okay, we have here positive numbers, A, B, C, D, E. We have here A, B, C, D, F. And now let us calculate these parallel transports and equate them. So here we have D over AE, 1, 1, 0, times 1, 1, 0, C over EB should be equal to 1, 1, 0, F over AB. So simple multiplication exercise. So this is equivalent to D over AE plus C over EB equal F over AB. And this is equivalent to DB plus AC equal EF. This is Ptolemy. So as soon as you have these rules of writing out the parallel transport operators, then the Ptolemy relation comes very easily. Yeah, okay, so we stop here, and next time we continue with those Penner coordinates, these lambda coordinates, and we will use them so to identify, to rewrite the symplectic structure, and gradually we will head to quantization and the construction of the basic algebraic system. Okay, do you have questions? Everything is clear? Good.